Welcome back to Machine Design course. We'll continue with static failure theories. In this slide, this video, we'll go through failure of brittle materials under a static load. In the previous video and lecture, we discussed different theories for ductile materials under a static load. So now we have the same type of load, which is static, but we have different materials. Brittle materials fracture rather than yield. So remember for the ductile material that we have a yield point and then it goes to a plastic region, but brittle materials fracture quickly. Brittle fracture in tension is considered to be due to the normal stress alone. Thus, the maximum normal stress theory is applicable in this case. So there is a different mechanism behind the failure of these materials, and that's why we need to use a different theory. So again, in tension, the normal stresses will cause the failure, and that's why we use a maximum normal stress theory. If you remember, we discussed maximum normal stress theory, but it was not a suitable theory for ductile materials. Brittle fracture in compression is due to some combination of normal compressive stress and shear stress, and requires a different theory of failure. To account loading conditions, and a combination of theories is used. So we'll discuss this in coming slides. Now, brittle materials could be either even or uneven materials. So for example, road materials are even. What are even materials? Compressive strengths are equal with the tensile strengths. And many cast materials are brittle, but they are uneven brittle materials. Compressive strengths are much greater than their tensile strengths, and these are called uneven materials. So when the compressive and tensile strengths are equal, they are even materials, and when they are not equal, and usually compressive strengths are much higher than tensile strengths, then they are called uneven materials. Okay, so here we could see a tensile test and the compression test for one even material. So in this case, the ultimate tensile strengths and the ultimate compressive strengths are equal, but different sign, yes? So SUC is equal to minus SUT. And we deal mostly with ultimate tensile strengths in brittle materials instead of yield strengths. Okay, so you could see the differences in calculating, for example, safety factor for ductile material. We used to get the value of the yield strengths and use SY in our calculation. So it was not important for us to see what is the ultimate strength of the material, because the yield point was, let's say beginning of failure point for ductile material. But for brittle materials, we don't have SY, and we have SY, but we consider failure at the ultimate strength of the material. So here you could see the Mohr circle. X-axis sigma, y-axis is tau, and this is a Mohr circle for tensile test and the compression test. Both have exactly equal circles. So if we connect top or bottoms of these circles, we see the failure line. Okay, we call it failure line. Here we have a Mohr circle for the tensile and the compression tests for uneven materials, and in uneven materials, SUC is bigger than SUT. So that's why you see the Mohr circle in compression test is much bigger than the Mohr circle of the tensile test. And if we connect these two circles top to top and bottom to bottom, we will see these lines, and we call it failure lines. The Cullen-Mohr theory, the explained observations lead to the Cullen-Mohr theory of brittle materials and failure. What we mean by observation, we discussed that what is the mechanism behind failure for brittle materials in tensile and in compressive force and loads. And we said that normal stresses are the main reason of failure in tensile forces, and in compressive forces, both normal and shear stresses are reason of failure. So those observations will lead to the Cullen-Mohr theory. Figure shows the two-dimensional case plotted on the axis and normalized with the ultimate tensile strength. So we have a sigma 1 and sigma 3 plate. So it's very similar to the one that we had a ellipsoid for von Mises theory, okay, or the hexagonal for a maximum shear stress theory, okay. On this one, we need to first find 4 points. The first one is SUT. When the sigma 1 and sigma 3 both are positive, means that both of them are tensile stresses and the maximum value could be SUT. The next one is minus SUT, this point. Okay, this is for uneven material. If the material is even, the point will be minus SUT because SUC is equal to SUT. The next point is SUT minus SUC, and the next point is minus SUC minus SUC. So you see that SUC is bigger than SUT, and you see that the maximum of the stress in the negative region is SUC, and the maximum in the positive region is SUT. Okay, now you have the square, either this one or this one. Okay, and now we could have two theories. The first one is Cullen-Mohr theory. The Cullen-Mohr theory connects this point to this point. So you see in the first quarter, because both of the stresses are positive, we use a maximum normal stress theory. So we're gonna leave it untouched, and we have the square. In the negative one, in the basically the second or fourth quarter, because one of the stresses are negative, then we need to find a failure line, and the failure line, we could find a failure line in sigma 1 and sigma 3 plane by connecting this point to this point. So you see the difference between the Cullen-Mohr theory and the modified Mohr theory. In the modified Mohr theory, we connect the corner of the this square, this dash square to this point, the intersection of um, the y-axis with this horizontal line, and also here. So this one, this line belongs to Cullen-Moore theory, and this line belongs to the modified Moore theory. Okay, but the original theory is the Cullen-Moore theory, and it comes from the fact that both shear stresses and normal stresses are behind the failure or main reasons of failure in second and fourth quarter, because we have also compressive forces. And we see later why we have modified Moore theory in the coming slides. Okay, so what happens after the Cullen-Moore theory, this one, is developed? Then people start to do some experimental tests to see the validity of the theory. Once they started to do tests, they saw that failure always doesn't happen in that region. And basically, they found a better theory or more accurate theory, which is a modified Moore Cullen theory, which is more based on the empirical data. Okay, so these are the failure points for the gray cast iron, and they found out that the modified Moore theory could predict the failure with the better accuracy. Of course, the Cullen-Moore theory, this one, is more conservative, you could see, because it's inside the other one. Okay, so the Cullen-Moore theory is still is valid, could be used, but if we are looking for a better accuracy, then we need to go with the modified Moore theory. Okay, so very similar, I could say. This is an analogy between these two theories and von Mises theory and maximum shear stress theory for ductile material. The maximum shear stress theory was more conservative than the von Mises theory, but the von Mises theory was more accurate. Okay? And this one is exactly the same. Cullen-Moore theory is more conservative, but the modified Cullen-Moore theory is more accurate. And this is all based on the experimental data. Okay? The modified Cullen-Moore theory is created and observed based on empirical data. The actual failure data shown in the figure follow the even materials maximum normal stress theory envelope down to the point of SUT minus SUC below the sigma 1 axis, and then follow a straight line to 0 minus SUC. Okay, so we are following this line. This set of lines shown as the combined light and dark color shaded portions is the modified Moore Cullen-Moore theory envelope. It's prefer failure theory for uneven brittle materials in static loading, just because it's more accurate, yes. But again, if we are looking for a more conservative theory, we could go with the modified Moore theory. And now let's see how we could do the calculation, how we could find the safety factor, and basically finding load line. Okay, so in real examples, when we find a sigma 1 and sigma 3, load line could happen to be in 3 regions. For example, could be at the point A. So when you find a sigma 1 and sigma 3, it could be in this region of point A, or it could be in point B and point C. So you see, when we let's say, increased applied or external loads, on this load line, we are intersecting a border at this point A prime. On this one, we have the intersection will happen at the point B prime, and for the C goes the C prime. So you see that mathematically we need different formula to find the safety factor for these regions. So I'm going to explain each of them. So if the 2D principal stresses are ordered, so sigma 1 more than sigma 3 and sigma 2 is 0, so it's a 2D case, so sigma 2 is 0, then only the first and the fourth quadrant need to be drawn, okay? So either the first or the fourth, which plots the stresses normalized by n divided by SUT, where n is the safety factor. Okay, so since this one is normalized, we see the border happens to be at 1, okay, and at 1 here. The figure depicts 3 plane stress conditions labeled A, B, and C. Point A represents any stress state in which the two non-zero principal stresses, sigma 1 and sigma 3, are positive. So A, when both of them are positive. And failure occurs when the load line OA crosses the failure envelope at A prime. The safety factor for this situation can be expressed as N is equal to SUT divided by sigma 1. So very simple, because the first quadrant follows the maximum normal stress theory and it's quite easy to calculate the safety factor. If the two non-zero principal stresses have a positive sign, then two possibilities exist for failure. Okay, so we have an opposite sign. Now we have two possibilities. As depicted by points B and C in figure, the only difference between these 2 points is the relative values of their two stress components, sigma 1 and sigma. Okay, so one of them is negative, the other one is positive, they have opposite sign. The load line OV exists, the failure envelope at B prime above the point SUT minus SUT, and the safety factor for this case is given by the above equation or same equation here. Okay, so safety factor is N is SUT divided by sigma 1. So if B prime happens to be above SUT minus SUT or this corner point here, then we could use the same formula. Okay, now we need to investigate for point C. If the stress state is depicted by point C, the intersection of the load line OC and the failure envelope occurs at C prime below point SUT minus SUT. So we are below this point, this corner point. The safety factor can be found by solving for the intersection between the load line OC and the failure line. This is the failure line. So we need to find the intersection of the OC line and the failure line. So if we do so, we could do that easily mathematically for unmodified Cullen-Moore theory. Okay, so for the unmodified one, the failure line is from here to here. Okay, this is the failure line. Okay, so if we connect this point to this point, we have a failure line for Cullen-Moore theory. Then we could use this formula for the safety factor. Okay, and for modified Moore, as you could see in this picture, we have The modified more, this is a failure line for the modified more, is exactly as what we have in this picture. Then the safety factor could be calculated by this formula. If the stress state is in the fourth quadrant, both equations should be checked and the smaller resulting safety factor used. So if it is difficult to, let's say, plot this figure, what you could do, you could use both of the formula, this one and the other one, which is SUT divided by sigma 1, calculate both safety factors, and then go for the smallest one. Okay, so this is basically one method to calculate safety factor for both a Cullen-Moore theory and the modified Cullen-Moore theory. Okay, what about effective stresses? As you remember, we had effective stresses for von Mises theory. To use the preferred modified Moore theory of above equation, it would be convenient to have expressions for an effective stress that would account for all the applied stresses and allow direct comparison to a material strength property, as was done for ductile materials with the von Mises stress. So you remember for the von Mises stress, we had the effective stress. Let's see if we could find that for this case. Effective stress involves the three principal stresses. So we need to find sigma 1, sigma 2, and sigma 3, and then we should calculate these constants, these constants, C1, C2, and C3. So these are three constants, and we need to calculate all of them. The largest of the set of 6 values, C1, C2, C3, plus the three principal stresses, I mean sigma 1, sigma 2, and sigma 3, is the desired effective stress. Okay, so what is our effective stress? Is maximum of C1, C2, C3, sigma 1, sigma 2, and sigma 3, where the signed function max denotes the algebraically largest of the 6 supplied arguments. Okay, so algebraically. Okay, so we are looking for the, let's say, the maximum value. That will be the effective stress. This modified more effective stress can now be compared to the ultimate tensile strengths of the material to determine a safety factor. So if we calculate the effective stress, then we could use this formula for the safety factor. N is SUT divided by sigma prime. Don't lose the larger picture. When the safety factor is more than 1 or equal to 1, it means that we are in the safe region, we are inside the polygon. And once the safety factor is less than 1, it means that we are outside the safe region and the material will fail under those applied forces. Okay, let's go through this example. We had a similar example for the ductile material is a bracket. We have a force apply here. We have all the geometry here. The only difference is that the material here is brittle, is a class 50 grade cast iron. We have an ultimate tensile strength and ultimate compressive strength. Okay, and you see this is uneven material. SUC is bigger than SUT. Okay, the geometry and the force is same as the previous example, and the load is static, and we are in room condition. So if we go through the calculation of apply the stresses at the critical points of A and B, will end up with the same numbers that we had in the previous example. So I'm going to go through those calculation quick, and you see that what are apply the stresses at both point A and B. Okay, so for the point A, we have a sigma x, which is a normal stress due to the bending moment M. And we have a shear stress, which is because of the torsion torque. And these are exactly similar as the previous example, and you could see the stress element for the point A. Now you could use the Mohr circle to calculate a principal normal stresses, and principal shear stress again is similar to the previous example. Now it comes to the point to calculate the safety factor. We need to find the load line. So we found both sigma 1 and sigma 3. And the sigma 1 is 24.1, and the sigma 3 is -6, okay, almost. So we have load line here. We need to also find these corner points. This one is SUT point, and this one is basically SUC. So this corner, if I connect this corner, will be SUT, SUC. This point is SUT minus SUC. Now you could easily plot this profile and find the load line. Okay. Once you do so, you see that what is the intersection? Intersection happens to be with the vertical line, not the failure line, this one. Okay, so now we could easily use this formula of N is equal to SUT divided by sigma 1. Okay, but we could use effective stress. Okay, so if you are not willing to find the load line and plot the basically failure profile, you could find the effective stress by calculating these constants C1, C2, and C3. You just need to plug numbers here for sigma 1, sigma 2, SUT, and SUC for all of these. So you will find these numbers. Now you need to find a maximum of C1, C2, C3, sigma 1, sigma 2, and sigma 3. And you see that algebraically, this number is the maximum. Okay, 24,144. And now you could use this formula for the safety factor, which is SUT divided by effective stress. And you will end up with the same number, no surprise, yes? This is just one alternative method to do this. That was for the point A. So we are done with the point A. We could move on to the point B. For the point B, we have a bending shear stress, and that is equal to 4V divided by 3A. And we have also the torsion torque, and the maximum shear stress is equal to this number. You could use a Mohr circle and find the sigma 1 and the sigma 3 for this case. We have a pure shear stress, so for this case, sigma 1 will be equal to the tau max, and sigma 3 is equal to the minus tau max. So these calculations are exactly similar to the previous example for ductile material, nothing new. Now it comes to the calculation of safety factor for the point B. We need to find the point B and find the load line. And for the point B, it happens to be B prime. This is a B prime, or intersection with the profile happens to be exactly at the corner. So we could use the formula of N SUT divided by sigma 1, and the same safety factor is equal to 4.1 for the point B. So since the safety factor is bigger than point A, it means that point A is the most critical point for us. Or we could go through the alternative calculation and finding the effective stress. So we could find constants C1, C2, and C3. So you need to plug numbers of sigma 1, sigma 2, sigma 3, SUT, SUC into the formula and find these numbers. Once you have these numbers, now you could find maximum of C1, C2, C3, sigma 1, sigma 2, sigma 3. And if you do so, you will see that the effective stress will be 12,827 psi. And now you could use this formula for the safety factor of SUT divided by effective stress. And with no surprise, you will see that safety factor is equal to the previous calculations. Okay, so we are done with this example, and you see that it's quite straightforward for both ductile and brittle materials. The first part is to identify and calculating applied stresses. Then we need to use a Mohr circle to find a sigma 1, sigma 2, sigma 3, tau max. Then we need to select our proper failure theory and calculate the safety factor. And it's a very good practice also plot the safety region and load line and see where the intersection happens, and see if our calculation matches with our figure. Okay, now we have one exercise. I'm going to leave this exercise to you to solve. A differential stress element is subjected to the stresses sigma x, sigma y, and tau xy. Okay, so these are applied stresses on one stress element. Okay, so you need to plot the cube and just illustrate sigma x, sigma y, and tau xy. The material is uneven and has strengths of SUT, SY, and SUC. Be careful that you don't need SY. Okay, it's given, but you don't need that. Okay, because first, material is brittle and uneven. So uneven material, all uneven materials are brittle. So you don't need to use SY, and you will only deal with SUT and SUC. Calculate the safety factor and draw a sigma 1 and sigma 3 diagram showing the boundary for each theory with the stress state and load line for Cullen-Mohr theory and the modified Mohr theory. So you need to find first principal normal stresses. So use the Mohr circle to calculate sigma 1, sigma 2, and sigma 3. Once you calculated these numbers, now you could draw sigma 1 and sigma 3 diagram and then plot the polygon for both the Cullen-Mohr theory and the modified Mohr theory. Then you will find your applied point sigma 1, sigma 3, load line, intersection, and you could use both graphical method or effective stress method and compare the result of these two methods together to see if you have the same numbers. Okay. So I strongly recommend you to solve this exercise by yourself in home.